Okay, let's dive right into this explainer and shatter the illusion that matrices are just a giant spreadsheet of numbers. Sure, if you've been working with basic linear algebra, you know how to multiply these grids together. But to truly unlock advanced data science algorithms, we're going to have to look under the hood and really understand the physical geometry that these numbers represent.
So here's our roadmap for today. First, we're measuring matrices with the norm, then exploring matrix spaces. Third, we'll look at information density, which is matrix rank. Fourth, warping space with the determinant. And finally, the characteristic polynomial.
As the original author brilliantly puts it, mastering these concepts is a waypoint in your transformation from a linear algebra newbie to a linear algebra nobie. Honestly, this material is the absolute crucial bridge you need to truly grasp advanced machine learning algorithms. So, take a deep, calming breath, and let's get into it.
Section 1. Measuring matrices. The norm. Understanding the magnitude of a matrix.
What's really fascinating here is that the Frobenius norm offers us a single, neat number that reflects the overall magnitude of all the matrices elements. You compute it by just taking the square root of the sum of all the elements squared. But think about that alternate formula for a second. You can also calculate it using the trace, which is just the sum of the diagonal elements of the matrix times its transpose. It's this beautiful mathematical shortcut, mostly because each diagonal element of that multiplied matrix is essentially the dot product of each row with itself.
And the absolute crucial point to remember is that this isn't just abstract theory. Matrix norms have massive, real-world applications. Adding a matrix norm as a cost function to a minimization algorithm, that's literally the core of regularization in machine learning. It directly increases how well your models generalize to unseen data by stopping overfitting in its tracks. Oh, and it's also used to drastically reduce the data storage size of images by minimizing the mathematical distance between a compressed image and the original file, a real game changer.
Moving right along to Section 2, exploring matrix spaces, where the matrix can actually reach.
If you start conceptualizing a matrix as a set of column vectors, the column space is the infinite set of all possible linear weighted combinations of those columns. Think of it like this. It's the infinity of real-valued scalars, multiplying, stretching, and combining those specific vectors to reach entirely different points in geometric space.
If you visualize what a 1D column space actually looks like geometrically, it's pretty intuitive. If your matrix only has one single column, its column space is just a line passing right through the origin, stretching out arbitrarily long in both directions. It's a 1D subspace, completely regardless of how many dimensions the vector itself actually lives in.
But here's the catch. Having more columns doesn't automatically guarantee you a higher dimensional space. If your columns are linearly dependent, meaning one is just a scaled up or scaled down version of the other, well, you are trapped on that single 1D line. But independent columns, they unlock entirely new dimensions. You can get a 2D column space, an infinite plane, almost like a microscopic, infinitely expanding slice of paper, completely embedded within a 3D universe.
Now let's contrast the column space with its much more subtle counterpart, the null space. The column space essentially asks the question, hey, what coefficients in X produce vector B? That's our classic AX equals B scenario. The null space, on the other hand, asks what coefficients in Y will perfectly balance everything out and produce a vector of all zeros, AY equals 0.
There is a deeply fascinating geometric relationship here. The null space and the row space are perfectly perpendicular. The dot product between each row and the null space vector is exactly 0. And here is a super handy rule of thumb. Full-rank matrices, where the columns are all totally independent, have completely empty null spaces.
Section 3. Information density, matrix rank. Redundancy versus independence.
Matrix rank is formally defined as the number of dimensions containing actual unique information in the matrix. Basically, it's the largest number of columns, or rows, that form a linearly independent set. In everyday terms, rank just tells us the physical dimensionality of the column space we were just talking about. It is always a non-negative integer, and it's a completely inherent, baked-in feature of the matrix itself.
You'll want to keep the ranks of these special matrices in the back of your mind. Vectors, they have a rank of 1. The zeros matrix has a rank of 0. An identity matrix has a rank equal to its total number of rows. But focus particularly on random matrices. If you populate a matrix using floating point numbers generated by a computer, it's usually going to have the maximum possible rank. I mean, the odds of accidentally creating exact linear dependencies with random floats are astronomically unlikely. As the source material jokes, it's so unlikely it could literally power the infinite improbability drive from The Hitchhiker's Guide to the Galaxy. However, as we all know, theory and practice often collide head-on. In the real world, computer rounding errors and tiny amounts of sensor noise mean that a matrix that really should be rank 2 might technically compute as full rank. Software programs like Python actually account for this. They estimate rank using a tolerance threshold on singular values, making sure that a tiny bit of random variance doesn't completely throw off your entire data analysis. Which leads us to a pretty critical question. In this messy, noisy real world, how do we actually mathematically verify if a specific vector lives inside the column space of a given matrix? And believe me, this isn't just an academic exercise. It's the fundamental logic that underlies ANOVAs, least squares regressions, and general linear models.
The logic behind this test is remarkably elegant. Step 1, you augment the matrix with the vector. Literally just stick it on the right side. Step 2, you compute the rank of the original matrix and then the rank of your newly augmented matrix. And finally, step 3, you just compare the two. If the rank stays the exact same, that new vector was totally redundant and already lives in the column space. But if the rank increases by 1, boom, that vector brought completely new information to the table and sits squarely outside the space.
Moving to Section 4, Warping Space, the Determinant, the matrice's geometric impact. Now, while it's heavily used algebraically to find inverses, I want you to think of the determinant geometrically. Think of it as a pure measure of spatial transformation. It tells us exactly how much the matrix stretches or shrinks vectors during multiplication. And get this, if the determinant happens to be negative, it actually indicates that one axis is entirely rotated or flipped during the transformation. Crazy, right?
Imagine squashing a 3D ball completely flat into a 2D disk. That is exactly what a zero determinant does to space. The transformation completely flattens at least one dimension, resulting in a singular reduced rank matrix. You might still have surface area, sure, but you have absolutely zero volume. It's totally flattened out.
And finally, Section 5, the characteristic polynomial, fusing determinants with matrix shifting.
Consider this truly fascinating equation. The determinant of matrix A minus lambda times the identity matrix equals delta. By simply shifting the diagonal of our matrix by some unknown scalar called lambda, we can somehow express the entire square matrix as a single polynomial equation.
And this right here is where the magic happens. If we run the algebra for a standard 2x2 matrix, we can find the specific values of lambda that make this shifted matrix reduced rank, meaning we are intentionally forcing the determinant to become exactly zero. Solving this equation reveals the fundamental roots of the matrix, what we call the eigenvalues. It provides the truly remarkable insight that literally every square matrix out there can be expressed as an equation with solvable roots.
So, you now know how to uncover a matrix's hidden eigenvalues by exploring its spaces, its rank, and its determinant. But the real million-dollar question is this. If the characteristic polynomial unlocks these structural secrets, how will you use them to revolutionize your data science algorithms in the future? That is exactly what you'll discover as you dive deeper into the world of machine learning. But for now, congratulations, you are officially a linear algebra newbie.